Good morning, everyone. My name is Nikos. I'm a second-year PhD student under the supervision of Andrea Cini. And today I will present you my PhD work, which is about surrogate-assisted structure optimization framework for optimization of composite airframes. Now, starting with the motivation, during the early stage of design, we usually have a lot of design freedom, but we also have limited knowledge about our problem. Now, later, when we gain more knowledge, usually the design is much more fixed and making changes becomes increasingly harder. So if we make some bad decisions early, usually these propagate to the final design. Now, the problem is that during the conceptual stage, these decisions are usually made with empirical rules or with old designs. So although these methods are fast, they are also sometimes not sufficient for novel designs or composite structures. A possible solution would be to use physics-based or finite element simulations and optimization from earlier on. But we have two main problems with this. The first one being that generating a detailed model manually is something that is tedious and very slow, and also running multiple optimization is very computationally expensive. So the main question is, can we efficiently use finite element models for design exploration from early? Now, my work is focused around three gaps. The first one being automation, that the fact that there are very few workflows that allow us to have parametric GFEM generation and also implement it in a broader optimization framework. The second gap deals with coupled structural layout and sizing optimization, which is rarely seen in the literature because it's a difficult optimization problem to solve. And last, we need methods that are able to optimize our structure in a data-efficient way because our evaluations are very computationally expensive. So to sum up, the PhD objective is to develop a framework that allows us to do surrogate-based optimization in composite airframes with finite element models. So this will be done in 3 steps. First, we create a Python framework that allows us to do the parametric GFEM generation. Then we will use surrogate models in order to reduce the computational cost. And in the end, we will use the surrogate model for Bayesian optimization. Starting from the tool, the workflow is implemented in Python. We have some inputs like the geometry, layout, properties, boundary condition, loads, etc. This creates a TCL script, which is a hypermesh command language. And in turn, this creates the finite element model and automatically sets up the sizing optimization if we so want. On the right, you can see some example of different wing models that the tool can create and also a fuselage model. Now, for the rest of the presentation, I will focus on an application on a wing box, which is part of the work I presented in the conference. So the main question here is, can we solve the coupled layout and sizing optimization problem using surrogate-based optimization in a nested loop? The model I will be using is the simple transonic wing developed by Gray in 2024. We have a total of 9 different components, and the model is generated automatically here in 2D finite element mesh with a tool. And we have 2 load cases, a 2.5G pull up and a -1G pull down that we consider. Regarding the nested formulation, basically we have an outer loop for the layout variables that are 3 in this case, the number of ribs, the number of stringers, and the width of the spark caps. And for every outer loop, we run an inner loop sizing optimization that has a total of 75 variables for the 3 optimization zones that we split the wing, that are mainly composite ply thicknesses and also some rib thicknesses. Now, the objective is to find the minimum feasible mass, which is done through OptiStruct gradient-based optimization. And for this reason, we run multiple runs because we have the local minima problem. Now, the constraints they are composite strains, aluminum stresses, buckling, and also some manufacturing constraints. So the surrogate model is formulated on the outer loop response, which means that it maps the layout variables to the minimized mass, effectively substituting the composite sizing optimization. More specifically, we use Gaussian process regression, which provides us with means and uncertainty prediction, and it's a good fit here because we have limited data and also enables Bayesian optimization. We start from an initial dataset of 12 layouts generated with Light-in hypercube sampling method to be as space-filling as possible. And after training the model, we can see the parity plot, which is the predicted structural mass over the true structural mass. And the closest the points are on the line, the better the fit. Looking at the errors, we have generally low errors and a high R squared, which means that the model fits the data very well. Now, I should also make a quick note here that the fact that we have low errors doesn't mean that the model is good. It just means that it fits the data well. And in this case, I believe that it underestimates the actual variability from the local minima. Before I go into the Bayesian optimization, I would also like to show the partial dependence plot, which basically shows us the model belief of how the mass changes for the three layout parameters. And we can quickly see that it sees that increasing the number of stringers or the width of the spark caps generally decreases the mass, whereas for the RIPs we have a non-monotonic and behavior and a weaker influence overall. Now, the Bayesian optimization loop basically works by using the GP model in order to evaluate the expected improvement, which is a quantity based on the improvement probability times the improvement amount. And if we maximize this, we can select the next layouts to evaluate based on either exploitation of good regions or exploration of uncertain ones. After the Bayesian optimization, which is run for a total of 18 more layouts, we concluded to have the best layout of 13 RIPs, 23 RIPs, 13 stringers, and a spark up width of 50 millimeters. And in the parity plot, you can see the orange dots being the new infill points. Now, I would like to make two quick remarks. The first one being that the orange points, the new points, are mostly clustered towards the low mass regions as expected. And the second one is that the updated errors are actually larger than before, which was something that we kind of expected because the previous model was overconfident, and I believe that this is a more realistic error estimate. Now, in the end, we also compared the results with Global Solver, a derivative-free revolutionary algorithm, and we see that the Global Solver converges to eventually the same, effectively the same layout, but it used 5 times higher the number of evaluations. So to conclude, we return to the original goals, and for the automation part, we created the parametric GFEM generation tool. We also introduced a nested optimization for the coupled layout and sizing problem, and we reduced the cost by training a surrogate and implementing Bayesian optimization. For the next steps, I would like to investigate other formulations to solve the problem, which are, for example, scalable surrogate models or constrained Bayesian optimization, which will be trained in analysis data rather than sizing. I would like to include laminate stacking sequence, which is important, and potentially expand the framework to include the fuselage. You can also see some dissemination achievements and some planned conferences, but in principle, that's all. Thank you.